All right, so we just found the stiffness of a 5/8 inch bolt with a 1 inch approximate grip length. Now let's find the stiffness of the members within the grip. So theoretically, the members are a little bit trickier to analyze because the pressure distribution under the head of the bolt is a little bit more challenging. It's not easy to calculate analytically. We make some assumptions, assume that it spreads out in a cone shape, that the stresses are even across this cone. But in our case, let's see, our case back here, we're going through two pieces of steel. The hitch is made of cast steel. The trailer is also made of steel. And the washer, we're going to assume, is made of steel. So if we're going through the same material, then the equations turn out to simplify. And there's two ways that you can go about it. You can use, this equation is given by Shigley. It's making assumptions about the diameter of the washer face being 50% greater than the fastener diameter. And so they plug that into their more general equations and they get this result. So that's one way that we can do it. We can also use this exponential curve fit from a study that was done using finite element analysis. And finally, we'll do some finite element analysis ourselves in order to estimate the member stiffness. Now, you really only have to do one of these methods. I'm just doing it to show that they kind of agree with one another. Okay, so let's collect all the information that we need in order to use this equation. The stiffness of the member is 0.5774 times pi times E. E is the Young's modulus, and D is the diameter of the bolt, the major diameter, and L down here is the grip length. We've got all that information already, so it's a simple matter of plugging and chugging. So K sub M is 0.5774 pi. E is 30 times 10 to the 6. D is 5/8 inch. All over 2 natural log of 5 times this L here is the grip length. At D, that's 5/8 inches on the top and the bottom. Okay, so a lot of computation to do, but if you plug and chug, you'll find that the answer is 22,185,285 pounds per inch of compression of that material, much stiffer than the bolt is. So this is method 1, kind of the analytical approach. 2 is kind of based on FEA, but it's like pre-tabulated curve fit. We're going to use this equation that Km over ED is equal to A, which we'll see what it is in a second, exp, that means the exponential function, that is e to the power of BD over L. And B we'll need to define. So A and B, we don't know what they are yet. D is the major diameter of the bolt. L is the grip length as before. In order to find Km, we're just going to have to multiply both sides by ED. And we already know what E is, the Young's modulus. All right, this coefficient A and B, these coefficients, are given on the table on the following page. I guess that's table 8.8. So for steel, the A coefficient is 0.7815, 0.78715, and the B is 0.62873. Our grip length, same as before, 1.095. Again, this is only valid if we're all going through the same material everywhere. You can't use this equation if you're going through different materials, but we are. D is 5/8 inch, same here, and E 30 times 10 to the 6. Plugging all those in, I get 21,130,584 pounds per inch. So really close, actually, in the scheme of things. These are quite close. These are just approximations anyways, because we don't have great math for solving for the actual stress distribution across this. We've made some pretty sweeping assumptions in order to get this far with the formulas. And the third way, I want to show that this does agree with finite element analysis. So I'm going to do the finite element analysis for our case in particular. I'm going to do that by modeling both steel parts, well, also the washer. The hitch I'm going to model just as a cylinder with a hole in the middle. it doesn't really matter what the geometry is far away from the hole, right? The hole is kind of what matters in this local material. It doesn't matter so much what's outside here. So there's the hitch itself, a cylinder with a hole through it. I'm going to model the trailer the same way. I'm actually going to use the same part in SolidWorks. Both of them are going to be 1/2 inch thick, and I'm just going to make cylinders because it really shouldn't matter what's out here, what the stress distribution is inside. And then the washer I'll make also a cylinder, but it's going to be of a different thickness and it's going to be of a different diameter. And what I'm going to do is I'm going to apply over an area that's equal to the area of the head of the bolt. I'm going to apply a fixed displacement actually because my intuition tells me that an assumption of a constant deflection over that area is more reasonable than a constant pressure applied over that area. I suppose either one is an assumption, but I'm going to go with the equal deflection over that area assumption. If you didn't want to make any assumptions, you'd have to somehow model the contact between the head of the bolt and the member surface and somehow apply some sort of tension inside the bolt. And I think we'll get a close enough result even if we don't go through that trouble. And same thing with the nut. It'll be close enough for analysis and you're going to see that it agrees with these equations. Okay, so we're going to have 3 cylinders. Let's get to work modeling those. I'm going to make these about 3 inches in diameter. It's substantially larger than the size of the hole, so that's all that we're really interested in. We're going to model the hole as though it's the same diameter as the bolt, just for simplicity, 5/8 inch. You could be a little bit more careful if you wanted to, but 5/8 inch is good enough. And I think that's actually the assumption that's made in Shigley effectively. It's basically saying that the diameter of the hole here, this D here, is the major diameter of the bolt. That's the other parameter in our equation. So implicitly, I'm not sure if it's stated explicitly here, but they're kind of assuming that the hole is equal to the major diameter of the bolt. So I'm going to do the same thing. We said it was going to be 1/2 inch thick. Okay, save that. I'm also going to save a copy of it for the washer, and I'm just going to change those dimensions. The washer outer diameter we can get from Shigley, the back of the book here. That also shouldn't matter too much, but we might as well be accurate with it. We were using the 5/8 inch with a thickness of 0.095, and the washer OD was 1.312. And the inner diameter, 0.65, that's really close to 0.63, so we're just going to leave that. Make this 0.095. All right, there's our washer. Now, in order to do the analysis, we need to we're going to only apply it over a fraction of this washer, where the head of the bolt doesn't contact all over the washer. So I need to separate the surface into 2 parts. So I'm going to make a sketch on top of this surface. And it says in Shigley that the head of the bolt is about 1.5 times the major diameter of the bolt. So let's go ahead and put that. 1.5 times 5/8. Okay, done with that sketch. What we need to do is take this surface and we're going to split it using split line. So it selected that face. I need to select this contour, and now I've got 2 separate surfaces on the face of my washer. So let's save this. I'm going to go back and do the same thing on the other part. So make it an assembly from this file, make assembly from part. I'm going to put the washer in first because it's facing the direction that I want. So that part's going to be fixed. Let's insert the hitch twice. Line them up. Make sure these faces touch. I'm going to go ahead and start by aligning that face with that one. But I'm going to flip that around. Nope. There we go. Now I'm going to try aligning these. Much better. Okay, so I've got my split face on the bottom there, and I got my split face on the top there. No more mates. So then we go into SolidWorks Simulation. I'm going to use a static study and use a 2D simplification. This is going to speed things up and make them look a little bit better. because this really is going to be a two-dimensional problem when you think about it. When you consider the symmetry, we only need to look at a cross section because it's symmetric all the way around. Well, before I do that, I actually want to add to the model an axis. So in the assembly, I'm going to make some reference geometry. I'll give it an axis. That'll be helpful. And all right, in the simulation, let's create that study. Use 2D simplification. And the plane that I want to use, I'll use this plane. So that's going to allow us to look at either of these two halves. But actually, no, I want to make it axisymmetric, not plane stress. Axisymmetric, using that plane, and I want to use this axis here. So now we're only going to be analyzing this portion because it's the same all the way around. All right, notice it's already add component contacts for us at these lines, so we don't have to take care of those interfaces. All we need to do now is apply these deflections. So I'm going to do that by first, in my fixtures, I'll create a roller or slider. This is the sort of contact I want, right? A kind of a sliding contact at this interface. This is the portion where the nut contacts the trailer. So we're going to fix that along translation in this, well, you can see here on the up and down direction by those green arrows in the y direction. But it's free to slide right and left. We don't want to fix all those material points in place to the right and to the left and into and out of the page. When we compress this material, it needs to be free to expand because of Poisson's ratio. All right, we're going to now apply in external loads, we can do a prescribed displacement. We're going to tell this, all right, I want you to translate by a certain amount. I'm going to use as our reference geometry, I'm going to use the axis here. This is going to tell us what direction to go. In the z-axis there, I'm going to prescribe a displacement of 1/10,000th of an inch, so acting downwards. All right, the last thing, let's apply some materials. Now, the nice thing about this method is you could apply multiple materials, and that'll really simplify your analysis of things. Let's actually select the parts first before we apply material. I'm just going to use alloy steel. It doesn't really matter. All that matters is the elastic ratio modulus. So that applied it to all three of the parts. They're now all alloy steel. And let's create the mesh. This isn't going to take very long, so I'm just going to make it a real fine mesh. It looks pretty good to me. What you can do is you can do a mesh refinement study. You can start with a coarse mesh and then get finer and finer and see if the results change much. If they don't change very much, then it's probably good enough. So this is the deformed shape. I don't want to see it like that. Let's see it without the deformation. You can see the stresses in here, but I think that the most useful stress, we want to kind of see the compressive stress. This is the von Mises stress that it shows by default, and you can kind of see that it's spreading out. The book doesn't actually say that it's going to look like a perfect cone. I mean, it makes the assumption that it's going to be constant throughout all these cross sections. That's just not what happens in practice. That's, it's actually more higher stresses in the center than there are on the outside. But we can kind of see the lines. If we want to just look at that primary compressive stress, well, then we look at the third principal stress, right? The first principal stress is going to be the most tensile, the most positive stress, and the third principal stress is going to be the most compressive, the most negative stress, principal stress. And so let's look at that third principal stress, and that will give us an idea of the direction of that most compressive stress. So I'm going to go to edit the definition of this plot. I'm going to change from a von Mises stress to a third principal stress, and I find it useful to show it as a vector plot. Now I'm going to bump up the size of these so that we can see things a little bit better. My vector plot options, I'll make these a lot bigger. And now you can start to see that cone shape that we expected. Now we've got some funny business going on up here. That's kind of probably at the intersection where the surface that I'm applying the load to actually meets the rest of the part. So I wouldn't necessarily trust the stresses in that area, but I do see that we've got sort of a cone shape. We're going kind of out at an angle, and you could tell me that this was 30 degrees on average, and I'd believe you, and that's kind of what it tells you in the book. And then in approximately the middle, they meet up, and you see sort of a symmetric sort of thing on the bottom. So that's what's really going on with this cone-shaped pressure distribution that they pretend in the book. All right, so we applied a given displacement. We want to know what force was causing that displacement, and that'll help us tell what the stiffness is. We can do that by going to Result Advisor. We're going to list the result force that's applied right here, and I want that to be in a particular direction. Oh, yep, I think that's all I needed to do is select that edge. And we see that in the y direction, or the negative y direction, we've got a force of negative 9,098. Now that's in newtons. Let's change it from SI units to English units. Update that. Okay, 2,045 pounds. So in SolidWorks, it took 2,045 pounds as a force applied, 2,045 pounds, and the deflection was 0.0001 inches. And if you do the multiplication, you'll find out that the stiffness, which is the load required for that displacement, divided by that displacement, I should say, is 20,450,000 pounds per inch, which is pretty close to what we got using both of these methods. We're all kind of centered around this value. These are all just kind of approximations, so you might guess that the SolidWorks one would be the most accurate, but it's fine for our class to use either of these two, or I'll tell you which one to use so that you get the same number so you can check your results on a given problem. But the nice thing about SolidWorks is that it's more flexible, right? I can very easily change the materials and make the geometry exactly what I have in my problem, and finite element analysis without some guess, some estimate that you can get by hand. So it's always a good idea to do both and make sure you didn't mess up. That helps you check your work when you do the finite element analysis. Make sure you didn't do something wrong somewhere.